session. We still have some exciting talks in front of us. So Anatoly will tell us about Cardy's variational ansatz, TCSA, and phase structure of QFTs. So please.
Thank you. And I'd like to thank all the organizers for making this wonderful workshop happen. I'm really enjoying all the talks and I've learned a lot. So this talk is based on the paper which is in the archive, and it has lots of details, but I'll try to stick to discussing some conceptual issues. So broadly speaking, I'm interested in taking a CFT, and I'll be working in two Euclidean dimensions. And I'm interested in perturbing it by a bunch of relevant operators, taking some generic perturbation, well, taking all perturbations, all possible perturbations, and then studying the space of flows. And so I'm not interested in solving these theories because generically I won't have integrability or symmetries or actually anything. But I'd like to understand the topology and geometry of the space of flows. And one tool which seems to be fitted to these particular questions is the so-called renormalization group interface. The idea was proposed by Brunner and Rogenkamp, and in simple terms, you just switch on your perturbation on a half space. So in this picture, you can see an unperturbed CFT, your CFT to be, and then you switch on the perturbation, then you add all counter terms, renormalize it, and then if the perturbed theory flows in non-trivial conformal field theory in infrared, then you end up with a conformal interface between these two conformal theories. And so it's a nice picture, but in general, we know very little about conformal interfaces between CFTs with different central charge. So we have very few examples when we know, say, all of the conformal interfaces. The situation is better if your perturbed theory develops a mass gap, then what you effectively get in the far infrared is a conformal boundary condition. So we'll refer to this boundary condition as an RG boundary. And so if you have a unique vacuum, that will be an irreducible conformal boundary condition. If you have generate vacua, then it will be a superposition of some conformal boundary conditions. And we know a lot more about conformal boundary conditions. For example, for Virasoro minimal models, we know all of that. They're given by the Cardy construction. And more generally, for rational conformal field theories, if you stick to symmetry preserving conformal boundary conditions, we also know how to construct all of them.
Excuse me, what's the distinction? I just regard interface as a boundary condition for folded CFT. It's the same problem.
It's a technical problem, so you can do it, but your central charge, even between two minimal models, central charge will be larger than one. So there are tons of them. Yeah. And so that was one construction where the boundary was introduced by hand. It just perturbed in a half space. There's another way to look at it, which I personally find it more pedagogical. Let me put my theory on a circle, my bulk theory on a circle. So then my Euclidean time runs horizontally, so I live on the cylinder, Euclidean cylinder, and then I can describe the states in my theory using the Euclidean functional integral. Suppose I have a fundamental field and I have some action, then I can impose Dirichlet boundary condition on some fixed circle here, and then say the vacuum wave functional will be given by taking a path integral on a half cylinder.
Is it obvious how to do this for like a general CFT, or is this just
I'll get to it, yeah. So I'm just starting with something familiar. I mean, people who studied, say, Polchinski's book, then the state operator correspondence in Polchinski's book is described in terms of a functional integral on a disk, right? So here I'm on a cylinder, but half cylinder is essentially the same as half disk. But the construction is much older than Polchinski's book, so it was introduced by Semantic in 1981. And there's also a nice article by Lusher who explains the semantics paper and also points to the connections of this construction with boundary critical phenomena. So imagine now that S0 action describes your conformal field theory, then you can perturb it by shifting the action by delta S, and then you can expand the perturbation into powers of delta S that will give you the functional integral with some insertions. So this will be equivalent to expanding the wave functional for the vacuum of the perturbed theory in terms of the states in the unperturbed CFT. And then, of course, you don't have to have a fundamental field. You can do it, say, in conformal perturbation. So then, instead of that functional integral, I just insert my operators, local operators, and instead of the Dirichlet boundary condition, I just choose the unperturbed theory state. So this correlation function now will give me the overlap of the perturbed theory vacuum with the chosen unperturbed theory state. And in this picture, you see if I take now radius very large, that will be equivalent to flowing with RG flow, and then this whole perturbed half cylinder will look like a boundary, provided my theory is gapped. So that I can state that asymptotically, the perturbed theory vacuum should look like a boundary state, conformal boundary state. And say for minimal models, we know exactly how they look like, these conformal boundary states. And when I wrote this wiggle here, that just means that it's for infinite radius. For finite radius, one should expect some corrections, and that I'll discuss in the next slides. Yes?
How can I see that this is a two-point function?
Two-point function. No, there is vacuum. I mean, you have to have some boundary conditions here taken at infinity. Yeah, and then you insert.
I think he's asking how is it then over?
Yeah, I know what that means.
Well, because this whole integral is over this space is my perturbed vacuum, and the boundary condition just takes a particular overlap. You know, in the wave functional, choosing the Dirichlet condition is just choosing a particular basis where the field operator is diagonal fundamental field. So I can choose some other basis here. Yeah.
Maybe it's a naive question, but when you do this perturbation,
Yeah.
I presume there's some conformal symmetry left on the left. Otherwise,
Of course.
yeah,
The left is
there's some
unperturbed.
local.
The left is unperturbed, yeah.
Right.
So this is just all of this was
But
to show you that
Can you
the
find it globally? I mean, would
no,
you run
it's
into
broken
any
here.
trouble?
It's broken here.
Right, but
So
there's
So
some
it will only reemerge. It will only reemerge in the extreme radius, in the form of the conformal boundary condition.
Right, but the question is it really exact on the left? You don't have any problem finding global transformation, which is, I mean, there's some.
What do you mean?
There's
I can look at
I'm
local
worried,
quantum
you know,
field
when-
theory, and I have my local currents, which will be, of course, conserved on the left.
Exactly.
But currents locally conserved. But spontaneously, the symmetry, of course, is broken because I don't even have the boundary for finite R. I have some interface between a conformal and master theory.
I guess I'm worried that it's a global symmetry which you somehow break only half of it. I'm worried that
This-
it will impact
all
the-
questions to symmetric, please. You know, that's I'm doing something really.
It's well
I'm
understood
just
by
doing-
those who understand it well.
Well, he didn't use conformal symmetry, right? But in the limit of very large R, it should emerge in the form of the conformal boundary.
So could I ask one question? If you have had another global symmetry, then you might have degenerate vacua, right? So
Yeah.
So then can I understand that all the possible vacua from the boundary states of the unconformed CFT? Is that a
That's a claim. Yeah.
Okay.
If I know all of them. Okay, so this was just kind of length explanation why the boundary emerges from the bulk theory, and for that sort of Lagrangian formalism was useful, and I see the locality of the boundary condition in the picture. But of course, I can use the Hamiltonian language, where I start by the CFT Hamiltonian on the cylinder and then perturb it to study this problem. And then I get the following question that how does this space of perturbed theories, provided they become gapped, breaks into domains labeled by different RG boundaries. So one concrete example would be the two-dimensional Ising model perturbed by general perturbation. It has only two relevant operators. There's the thermal perturbation and the magnetic field. And it has three elementary conformal boundary conditions which correspond to the fixed spin, two fixed spin boundary conditions, and the free boundary condition, which is Z2 symmetric. And then the picture of the phase diagram is depicted here. So it's two-dimensional, so I have magnetic field vertically, thermal perturbation horizontally, and well, here each point defines two couplings, but of course I imagine that it's all foliated by RG trajectories. So the assignment just means that for all points here, if you go to the far infrared, you'll end up with the corresponding conformal boundary condition. So you see that generically you have the fixed spin. So whenever you have magnetic field switched on, you have a fixed spin boundary condition here and here. But they're different, and there is a special line of zero magnetic field which separates these two regions. And the blue line here is the symmetry breaking line. So here the boundary condition, if you write on this line, the boundary condition is not irreducible. There's a direct sum of plus and minus. And the red line is the disorder line. So here the Z2 symmetry is preserved. And the boundary condition right on this line is given by the free boundary condition. So you see this kind of general structure that each perturbation is assigned some boundary condition, but some sort of form, they reside on smaller dimension surfaces which separate larger dimension region.
So what does the boundary condition mean?
This is the superposition, like it's not an irreducible boundary condition, but just the direct sum.
So you're summing over both. So what does plus mean? You have
well,
plus,
the vacuum state
plus
will
one
be
on
degenerate. The vacuum state will be, so
Degenerate.
from the point of view of the bulk space is degenerate, and I have two boundary conditions which look different. So the vacuum subspace will be spanned by these two boundary states.
But on the field theory, what is the boundary condition?
On the
So
field? What is the so general question, what is the superposition of?
What is even the plus boundary condition? How do you define it? Plus.
It's a fixed spin boundary condition. So in free fermions you have psi equals plus or minus psi bar on the half plane, for example, kinetic model. One choice of sign is the fixed, another one is free, and you can distinguish them by say bulk one-point functions. So you can see that the magnetic fields for the free one, they have 0 one-point function, and they have positive or negative one-point function for plus and minus. So you can get your intuition. And yeah, so of course, I mean this is a free theory on this line, so you can solve it exactly, and you can exactly see how your vacuum becomes identified with these conformal boundary states, which are built from Shibashi states, which is the usual sort of CFT way of building them. But generically, you don't have any exact analytic methods. But you can use a numerical technique, which is what TCSA stands for. It's truncated conformal space approach. It was developed by Yurov and Zamolodchikov in 1990. So you take your perturbed Hamiltonian as an operator in the unperturbed theory state space, and that state space is built by taking primary fields and acting on them by Virasoro operators. And the momentum along the circle is also conserved, so I can restrict myself to any momentum sector, and typically people take just the zero momentum sector because this is where your vacuum state will be sitting. And then you, so this is an infinite dimensional matrix. You can calculate its matrix elements, but you restrict yourself to a finite dimensional subspace by saying that the total weight is less or equal than some truncation parameter. And then you put this matrix onto the machine, and then you numerically diagonalize it, and that gives you the eigenvectors and eigenvalues. So the lowest eigenvector will be a vacuum vector, and it will come with the, so if you choose an orthonormal basis of these states, then you can compare it to Cardy's boundary states, which are built from Shibashi states in a known way for many orthonormal bases. So this is kind of the setup one can study, but of course I'd like to understand the physics of it better. Namely, it's tempting to say, well, my conformal boundary conditions are labels for my bulk phases, but really, what do they have to do with the usual phases we know and love from thermodynamics and critical phenomena? And also, what about these transition surfaces? Or what happens on them in general? Are they always first order phase transitions or something else? So that's another question. But sort of the bigger motivation for me is sort of to try to imagine, can we build some analytic theory of critical phenomena which would replace the Landau theory, which has like a Lagrangian flavor to it, by something more algebraic, which would be suited to perturbed CFTs. So it would sort of describe critical phenomena in the language of the UV CFT, which has to be more algebraic. So it would be nice to have such theory because, for example, we don't have, we know lots of CFTs, we don't have for all of them, we don't understand the underlying lattice models, or even if we can write them, it doesn't help in establishing their phase diagram. So that would be, I think, interesting to develop such a thing. So what would be an analytic tool here which would replace the Landau functional? I'm trying to develop the ansatz, variational ansatz, which Cardy proposed. So he said essentially that at finite R, the asymptotics of your vacuum state should look like this. It should look like your chosen conformal boundary state smeared by some translation along the cylinder. So here tau is some parameter which is dimensionful, so it will depend on your mass gap. And H0 is the unperturbed CFT Hamiltonian, which shifts this vector. Then you can look at the variational average. So take the expectation value of your perturbed Hamiltonian divided by the norm, and then you want to minimize this in tau and also in the discrete label of your conformal boundary state. And this construction is very nice in that, well, in particular in the fact that, so you can think of it as perturbing the boundary. So since H0 is an integral, wide integral of the stress energy tensor T, and you can think of this as some irrelevant perturbation of your boundary condition. So this will, the components will go as tau over R, and therefore, you know, at large R, it will go away, and you will end up exactly with the conformal boundary state. And such perturbation from the point of view of the boundary is always available. So in any conformal boundary condition, T is there, and it's an irrelevant operator because it has dimension 2. So for the boundary, marginal is dimension 1. So it's always there. And moreover, there is a nice geometric meaning of this variational average. It looks like just a bunch of one-point functions on a cylinder, which is kept by your conformal boundary condition. And the length of the cylinder is tau. So tau has a geometrical meaning. And then in the limit, tau much less than r, so defined for a limit, one obtains the following very concrete expression for this variational energy. So as a function of tau, it's just a linear combination of power functions. And so it's a bit more complicated than the Landau theory polynomials, but still quite a simple function. Moreover, you see the exact CFT data entering here. C is the central charge. Delta i's are the exact CFT dimensions. And AI, these coefficients here, they're one-point functions on the disk with the chosen conformal boundary conditions. So there's an input of the exact CFT data.
Sorry, what was lambda I again? No.
Lambda i's are my coupling constants, just coupling constants.
Of the theory that the coefficient of the conformal perturbation.
Yeah.
Okay.
Yeah. Perturbed by relevant operators is
Sorry.
Yeah. But there are some problems here. One problem Cardy noted himself is there's some UV sensitivity, while the low conformal weight components of the vacuum vector are captured often accurately, then the tail of the very high weight components sometimes look different from this exponential decay that Cardy's ansatz has in it. And sometimes the tail is important. It's important to calculate the correct energy, and also sometimes it's important for the correct expectation values of other operators. But it seems to be linked to ultraviolet divergences. So for example, on the Ising zero magnetic field line, you have a logarithmic divergence, and that seems to influence the UV tail, and it seems to be important. Another general problem is with the symmetry breaking in disordered region. So I have not a single functional, but I have several variational energies labeled by conformal boundary conditions. So when I'm in the disordered region, my boundary condition, the winning boundary condition, is the one which is described by the symmetry preserving boundary condition. And then the ones which are built on the symmetry breaking boundary conditions, they will have some kind of finite gap about that energy. But now if I switch on a small, can't carry the weight, should watch this out. So if I switch on a small bulk symmetry breaking perturbation, then my energy will, if it's very small, then still the symmetry preserving boundary condition will be winning. It will have the lowest energy. And that's a problem because once I break the symmetry, I expect some expectation values of the symmetry breaking operators. And I won't see it. So something needs to be done. And here, so I looked in detail at two examples. The Ising model, there it seems that the missing energy contribution sits in this UV tail. You can analyze that. But in other cases, like in the critical Ising, it can sit in the different ansatz which should describe the low weight components. So some modifications sometimes are needed. So the thing I'd like to add to the Cardy's analysis is the stability condition. So if you have a minimum, then it should be stable under some small perturbations. So you can modify this ansatz by switching on a boundary relevant operator. And then you will see, you look at the variational energy, And you'll see that the leading term, the leading change in the variational energy from that perturbation will come from bulk boundary OPE coefficients, and it will be linear in the coupling. So that you see if that term is there, then you can always choose the sign of your coupling so that whatever the signs are of the bulk boundary coefficients, it will bring the energy down. So then it will be a stable minimum, and so that gives us a certain condition which I boxed here, which comes from requiring the stability under perturbations of your minimum, variational minimum. So bulk boundary coefficients here are important. So this condition can be satisfied trivially if you have a stable boundary condition. So you have no relevant operators on the boundary at all, and that's the case in the Ising model in the bulk. So in fact, I claim, my current understanding is that the usual thermodynamical phases, they correspond to the stable conformal boundary conditions. Another way is that the boundary conditions are unstable, like for example the free boundary condition we saw in the Ising model, but the bulk boundary OPEs are all zero. This can happen as well, but more interestingly, this can happen in the third way when there are like a cancellation between different terms. So this happens for some fine-tuned RG trajectories. So I spell this out. So at the end of the day, you see, so if it is unstable and it comes with a relevant operator, you can associate the transition lines to pairs of boundary flows. So for the Ising model, on the disorder line, this boundary condition would be unstable if I switch on the bulk field. So when that happens, you effectively what you get, you induce a boundary RG flow, which comes from the boundary magnetic field operator. So here is this pair of boundary RG flows, which correspond to the red line, and with the blue line, you also have a pair of RG flows in both directions, which corresponds to switching on the identity fields on one of the components. So such flows are always there when you have a superposition. So tree-critical Ising model is offers kind of more interesting phenomena. So I do have an underlying lattice model, which essentially is a spin-one Ising model. So my discrete variable takes the value 0, +1, or -1. And with it, I get, one obtains 6 conformal boundary conditions, because there are 6 primaries in this theory. And you can think of them as 0 means like pinning down the lattice variable to be 0 on the boundary, +1, -1, +0, that's a new one. We didn't have this in the Ising. This is when on the boundary you can have either +1 or 0. Same for -0. And T is essentially a free boundary condition, but for historical reasons, it's denoted by D for disorder. I have, in the CFT UV, I have 4 relevant perturbations, 2 thermal, symmetry preserving, and 2 magnetic ones. So I've studied in detail first the perturbations by the 2 most relevant operators. So one most relevant thermal and the most relevant magnetic. And then here is the phase diagram. So we have a blue line, which is similar to the symmetry breaking line in the Ising model. And we have 2 new lines, which are the 2 red lines, which are labeled by these new boundary conditions, which is like a mix of plus and 0 and minus and 0. And it turns out that everywhere here in this region to the right of the red lines, the Cardy's ansatz doesn't work. So you can really look at your vacuum vector and it doesn't look like just the exponentials. It looks more complicated. So in the paper I proposed a different ansatz for describing it, and that has to do, the fact that there's an additional ansatz has to do with boundary irrelevant operators. whose dimension is less than 2. So it's a dimension 3.5 boundary relevant operator, so it's a special situation when this will be less irrelevant than T. So that, and it is symmetry breaking as well. So that gets switched on the boundary. And so, yeah, so I can obtain the position of the red lines analytically using this stability condition in the Cardy's ansatz. And then I check numerically that indeed on that particular G trajectory labeled by this dimensionless parameter, this discontinuous transition in the structure of the vacuum vector happens. But, and you can associate yeah, these 3 lines again with boundary RG flows. But if you want to get some kind of more physical picture rather than just looking at how the vacuum vector components look like, so more physical will be looking at more physical intuition you can get about this transition by looking at one-point functions on the plane. So, for example, the one-point function of the leading magnetic operator is just your magnetization. And you see that as you go across that red line, the magnetization profile looks like a kink. So that's, I like to, for lack of a better word, I refer to these new red lines as the kink transitions. And for other one-point functions, you also see that they look like there are some kind of smoothed out discontinuities there. And one might wonder, well, because I have finite size corrections and I have truncation errors, could it be that there's a real phase transition there, first order, second order, which is just smoothed out, but you can actually determine by this exponential, effective scaling exponential for the energy gap that that's not the case. The theory has a small mass gap but finite. So, yeah, more interesting stuff you obtain actually switching the third coupling, because then you get a whole theoretical surface, 2-dimensional surface in the 3 coupling space where these kink transitions happen. So there's a red line that now extends to this cool gray surface, and when you start moving along that surface, you see that your mass gap closes. So you discover in the end you arrive to the green line, which is a critical line, which is a symmetry breaking RG flow from the trifradicalizing to the Ising model. And so maybe I shouldn't skip the Landau theory. Yeah, I'll be happy to tell people in private. I have kind of a Landau theory interpretation of what these red kink lines are. But to summarize, so I did probe. So I've learned quite a few things about Cardy's ansatz. Often it does work quantitatively really well. You just measure the numbers and they fit your analytic calculations with the ansatz. Sometimes it needs a modification, but that happens in a particular situation. So by looking at various CFTs, you can hopefully guess. If you know your boundary conditions, you can guess when we need to modify it. And so to summarize what I've learned about the RG boundaries is that, yes, the analogs of thermodynamic phases seem to be the stable conformal boundary conditions. The unstable ones, they label transition surfaces, which could be first order phase transitions, where I would have a superposition of the boundaries, but there are more other ones where they're irreducible but unstable, so which give rise to my kink surfaces, and they give you some theoretical indication of where your new critical lines are. So I think there is a real utility in them because they restrict to the subspace where you search for critical lines, which is great because Cardy's ansatz initially was only for gap theories. So I had no information about the mass gap itself, but here I get some indications where I can search for the critical lines. So with that, I stop. Thank you.
Okay, questions for the closing time? There are.
So suppose someone want to do this for like higher dimension case, like maybe 2+1 dimension. What do
But
you what do you need to know before?
you need to,
running
I
the
would
program?
say, here the great advantage, I know all of the conformal boundary conditions.
I see.
So I don't know, you would know, I don't know, Dirichlet Neumann if you would do something like this for free field, but I don't know if, at least would to know all the stable ones. I mean, what's the current status? I don't know, some people are working on constructing new conformal boundary conditions in high dimensions, but I think we're still far from any kind of classification.
So you need to know that, and then maybe the dimension of those primaries.
Oh, that if you know that your QFT exactly, yeah, you will need to know all the data, like what I put here into the Cardy's ansatz, because in Cardy's paper it's written for d-dimensional case as well. So if you can extract that information, like one-point functions of bulk operators in those conformal boundary conditions.
Thank you.
Any more questions?